Okay, here is another problem that involves using work energy principles in the context of a constrained pulley system. Okay, here's the problem. Consider the pulley system from homework number 4. So this was a problem in homework number 4 where you had to solve for the accelerations of the masses using essentially F equals ma and free body diagrams. Okay, so that's the setup. You have a pulley, three pulleys, two masses, and all ideal pulleys and ideal inextensible strings. You have two masses, m1 and m2. You're told that initially the velocity of m1 is v10 downwards, v10 downwards. What is the final velocity v1f final of m1 when it has lowered, dropped down by height h? Okay, so you're told the initial velocity, downward velocity of m1. You're asked to find the final downward velocity of m1 after it's gone down by height h. Okay, so how do we solve this problem? Whenever you see us asking about what is the velocity or what is blah after not time t, but after things have moved by a distance h or something like that, you always want to think of work energy principles and essentially trading off kinetic energy and potential energy, because the height change is related to potential energy, and of course you can relate that to kinetic energy changes if there is nothing else that is doing work on the system. Okay, so how do we start? You've been told the initial velocity of m1, but you've not been told the initial velocity of m2. Okay, but we know from homework number 3 or 4 that the velocities of m1 and m2 are related. The accelerations of m1 and m2 are also related, and they're related by the fact that this string is a constant length string and this string is a constant length string. You can refer back to homework 3/4 to figure out how we computed a relationship between YA and YB. I think we essentially found that 4YB plus YA plus a whole bunch of constants equals a constant, which when differentiated gives 4YB dot plus YA dot equals 0. So this is actually the relationship between YB dot and YA dot. Okay, it's a relationship between this velocity and this velocity. So if you know YA or Y1 dot, you know Y2 dot. So we know the velocity of M2 as well given M1. So that's all good. Okay, now you've been told that the mass M1 lowers by a height h, but you've not been told what mass M2 does. And again, you use essentially the same relationship. If there is a relationship between the velocities YB dot and YA dot, essentially the same relationship exists between the displacements YB, delta YB and delta YA. Okay? Where delta, when we say delta YB, what we mean is YB final minus YB initial. Okay? So what this means is that if YB goes down by 1 unit, YA goes up by 4 units. That's what this relationship means. Okay, so once we've been given the displacement of mass m1, we also know the displacement of mass m2. So we know the two initial velocities. Essentially, we know the displacements, the vertical displacements of the two masses. Now we are all set to compute or use essentially delta KE plus delta PE equals 0. Okay, so here is a very important point regarding sign conventions, SIGN conventions. Okay, so we have defined here YA and YB to be downward positive, right? In other words, if YA increases, the mass goes down closer to the Earth. Okay, so the expression for potential energy is minus mgy if y is downward positive. the expression potential energy equals mgy is only true if y is measured upward. If y is measured downward, then we should use minus mgy. So this is very important. This is a common source of errors. So once you've realized that you're measuring y downward here, of course you could have chosen to measure y upward from some datum on the ground, like from draw a line here and then measure upward. That's possible, but that's more complicated. It's simpler to measure y downward like this. So just go with it. But then if you do that, write this um, somewhat non-standard expression for potential energy, essentially doing potential energy equals minus mgy. So what is the initial potential energy? It's minus m1 gyai. In other words, this is the potential energy of mass m1, initial potential energy of mass m2, and you just give them some notation. You don't know what the initial position is. You don't know what the initial position of B is. You just give it some y. And similarly, the final potential energy is minus m1 gyA minus m2 gyb. Because all that matters is the difference. So we don't need to know the actual y's. All we need to know is the difference between ya and y initial and y final. Okay, so we've gotten expressions for that. We've gotten expressions for the initial kinetic energy, which is half m1 v1 square or va square. Similarly, half m1 m2 v2 square or vb square, both initial, and then same for both final. And then we just use the energy conservation, which is initial PE plus K equals final PE plus KE, or delta PE equal plus delta KE equals 0, same thing. So we just plug everything in from these four equations into this equation. You can plug everything in, and then we can also use the fact that VB is basically VB is VA divided by 4 with a negative sign. So we use that. VB is VA divided by 4 with a negative sign. So you plug all those things in and do some simplifications. Essentially, we use the fact that y final minus y initial for mass 1, y final minus y initial for mass 1 is minus h, or y initial minus y final equals h because it goes down. So use all that and simplify. You get this expression, I guess. It's velocity of 1 final equals square root of velocity of 1 initial squared plus blah, 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 blah. Okay? So, and then we use the positive square root because we are saying essentially that the mass is going downwards. But basically, this looks slightly messy, but only because these are all algebraic quantities or essentially variables. If we gave you the initial velocity of mass 1 and the numerical value for h, the values of mass m1 and m2, this simplification will be very easy. So I'll just leave it at that. Okay, that's it.